of system of three charges. In last class, we discussed about the electric potential energy of system of two charges. Here in place of three charges, we took the two charges. With the help of two charges, what will be the electric potential energy? And before going to discuss about this electric potential energy of system of three charges, what we completed in last class, we revise it. That is conservative nature of the electric field. As we know that the work done by the force to complete the round trip of an object. So if you observe the diagram, there the charge is moving from initial point to the final point, and it completes one circle or one round trip or one closed path. So there we get the total work done is 0. Then work done by the force to complete one round is equal to 0. That we call that conservative forces. We know the examples for the conservative forces are gravitational force and the spring force, and now in that examples one more also will add, that is the electric field. So electric field is the conservative nature, and the potential energy, yesterday we discussed about the potential energy of system of charges. In that we have two types of potential energy of system of charges. One is that interaction of the potential energy between the charges. The second one is that self-energy, and the self-energy we discuss later. That is the additional topic that is not there in our syllabus. For competitive, we discuss briefly about the self-energy. But this potential energy we can discuss only in case of conservative forces. It is applicable only in case of conservative nature. So in that conservative nature, we got the formula also, that line integral of E bar dot dl is equals to 0. As the electric field is conservative, then for all the system, from initial point to the final point, we get that same result. It means it does not depend on the path. It is independent of the path, and it depends only the initial and final positions when we use that integration, line integral. Okay. So now the potential energy of the system of two charges, we got that U is equals to, U is the symbol for the potential energy, electric potential energy. The electric potential energy is U equals to 1 by 4 pi epsilon naught Q1 Q2 divided by R. And this is the electric potential energy of system of two charges in the absence of electric field. Initially there is no electric field. So if there is no external electric field, then to bring the charge, one of the charge, and for that we no need to do work done, and only to bring the charge Q2 we need to do the work, that is W2, and finally we add the total work to get the potential energy of system of two charges. And now is that potential energy, electric potential energy of system of three charges. And to get the three charges in the absence of external electric field, this is a very important one. In the absence of external electric field, what does it mean? It means initially there is no electric field. Without electric field, we are going to assemble three charges. Okay? So then, to bring the charge from infinite to the given point, am taking here the point is A. So at point A, we want to bring the charge. One of the charge is Q1. Q1 is the charge to bring into the point A. Then work done will be 0. Why work done is 0 here? Means that we are not doing any work to bring the charge from infinite to the given point, because there is no electric field and there is no opposing force on the charge, so that work done will be 0. So then we bring the charge Q1 and we place the charge Q1 at the point A. And now that what happens? The charge Q1 produces the field, electric field. We know that the charges, when the charges are at rest, it produces the electric field. Then this Q1 produces the electric field. So when it produces the electric field, we want to bring one more charge. For that, I will consider the charge Q. So we want to bring the charge Q2 to the point B, and the distance from Q1 to Q2 is, I am taking R1. R1 is the distance from Q1 to Q2. Now the charge Q2 we bring from infinity to the point B against the field. So if any external electric field is there, to bring the charge into that field, we need to do the work against the field. So then work done by the charge, the amount of work is required to bring the charge Q2 into that point B is W2. In taking that, work done W1 is equals to 0, because there is no external electric field. There is no external electric field. So that work done is 0 to bring the charge Q1 to the point A. And to bring the charge to point B is W2 and is equals to, and Q1 produces the electric field. Then work done by the charge Q2 due to Q1 will be, we write that the potential produced. We know mathematical relation, potential is equals to work done by the charge, then work done is equals to potential into the charge. But here this potential V1 is the potential produced by the charge Q1. So V1 into, we are going to bring the charges Q2. So then work done is W2 is equals to V1 into Q2. Then we know the potential. The formula of the potential is that 1 by 4 pi epsilon naught Q1 by the distance is R1, and we are going to bring the charges Q2 into that. So then work done to bring the charge Q2 into the field against the field, the W2 is equals to 1 by 4 pi epsilon naught Q1 Q2 by R. So we consider this is equation number 2 and this is equation number 1. Now we are going to bring one more charge. Here you see that electric potential energy of system of 3 charges. So two charges we assembled and one more charge we want to bring. So when we are bringing one more charge, that is third charge, into the field, here the field produced by the charge Q1 and the field produced by the charge Q2. These two will be effect on the third charge. So that we need to do work against these fields. So now I am going to bring the charge Q3 into this field. That point we consider C, and the charge is that Q3. And now the distance from Q1 to Q3, taking the distance is R3, and the distance from B to C is R2. So A to B the distance is R1, and B to C the distance is R2, and A to C the distance is R3. Okay, so like we are showing, representing with the dotted lines. So now we assemble all the charges, 3 charges. Then what is the work done to bring the charge Q3, that we are going to write. So then W3 is the work done to bring the charge into the field, given field, and that we are doing against, we are doing the work to the field, electric field. So W3 is that potential due to the charge Q1, that is V1, into the charge is Q3, V1 Q3 plus again the potential due to the charge Q2. So that potential is V2, and we are bringing the charge is that Q3. So work done to bring the charge Q3 into this field is V1 Q3 plus V2 Q3. Already we discussed how many charges are there, and those many potentials will be created by those charges. Here Q1 produces one potential, Q2 also produces the potential, and these two potentials affects on the charge Q3. So then work done will be V1 Q3 plus V2 Q3. And as we know the formula of the potential, that V1 is equals to 1 by 4 pi epsilon naught Q1 by the distance, that is from Q1 to Q3, the distance is that R3. So Q1 Q3 by R3 plus potential produced by the charge Q2 is 1 by 4 pi epsilon naught Q2, the charge is Q3, divided by the distance is that R2. Okay, this is the work done to bring the charge, third charge, into the field W3. Okay, so the total work done. Now we arrange all the 3 charges. Then what will be the total work done? To get the total work done, to assemble all the charges, the total work done. Total work done to assemble the charges are, that is W is equals to W1 plus W2 plus W3 is the total work done. Now we add all the work done, then work done W is equals to W1 is 0 plus W2 is that 1 by 4 pi epsilon naught Q1 Q2 by R1 plus W3 is 1 by 4 pi epsilon naught Q1 Q3 by R3 plus 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught Q2 Q3 by R2, Q2 Q3 divided by R2, that is the total work done. So in that, what is the common term? 1 by 4 pi epsilon naught is the common term. Then work done W is equals to 1 by 4 pi epsilon naught Q1 Q2 by R1 plus Q1 Q3 divided by R3 plus Q2 Q3 divided by R2. This is the total work done. And this work done is stored in the form of potential energy. So we are going to take the interaction between the charges, that interaction potential energy when the charges are separated. And one more is that here the potential energy depends on their charges, how much distance. It depends on separation between the charges, and it does not depends on their location, where they placed. It doesn't depend. It depends only the separation between the charges. Okay, that is the very important point regarding the potential energy. And this potential energy, we use the symbol U. U is equals to, here only mention, U is equals to W is equals to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught Q1 Q2 by R1 plus Q1 Q3 by R3 plus Q4 Q3 by R2. And one more, already I explained you that it is applicable only for the conservative forces. If the charges are like charges, then what happens? What type of potential energy? Is it negative or positive? Because the potential energy may be positive, may be negative, may be zero. If the charges are like charges, then what happens? We know that like charges repel with each other. For example, I am taking the two charges are like charges. The two charges are like charges and separated by the distance, and they repel with each other. So when the two charges are repelling with each other, then there the storing potential energy. That storing potential energy is in the form of kinetic energy. So when the charges are like charges, and the potential energy will be positive. If the charges are unlike charges, then what happens? I am taking one is the black and mark. You can observe clearly. So I am taking the two charges are unlike charges. Then attraction takes place. So when the attraction takes place, then the interaction will be more, and it is in the form of potential energy, and the total energy will be negative. So these 2 points are important. The first point is when the two charges are like charges, repulsion takes place and they move away from each other. The potential energy or the storing energy is in the form of kinetic energy, and the total energy will be positive. If the two charges are unlike charges, then attraction takes place and the potential energy also will be increases, and the total energy will be negative. Okay, these are the 2 points. And one more is it may be positive, it may be negative, or it may be zero. And one more is that the potential energy, if you observe clearly in case of 2-point charges and 3-point charges. In case of 2-point charges, we have got 1 by 4 pi epsilon naught Q1 Q2 by R. For 3 charges, system of 3 charges, 1 by 4 pi epsilon naught Q1 Q2 by R1, Q1 Q3 by R3, Q2 Q3 by R2. What we observe the difference in for the 3 charges and the 2 charges? The combination, all the pairs should be there while finding the potential energy. That combination is, to understand easily, the combination that is 1 by 4 pi epsilon naught Q1 Q3 by R3. This is one combination, and another combination is that Q1 Q2 is one combination, and Q2 Q3 combination. So all the combinations should be there while finding the potential energy. This is for the objective. We need to know these points. And one more is that while taking the charges, whatever the original sign of the charges, whether it is the positive charge or the negative charge, we must use the original sign of the charges. For example, taking the example, here the 3 charges. So at point A, the charge is that minus Q1. At point B is Q2 plus Q2, and at point 3 the charge is plus Q3. So like three different charges are assembled in the field. And then what will be the potential energy? So to write the potential energy, what I am saying that one is that all combinations should be there. And while writing the charges, we should use the original sign. And here from A to B, I am taking the distance is R1. And from B to C is R2. And A to C, the distance is that R3. Then potential energy U is equals to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Q1, here that Q1, Q2. The first combination is Q1, Q2. Here Q1 is negative. So minus Q1, Q2 divided by R1 plus. Then second combination is Q2, Q3. Both are positive. Then we write that Q2, Q3 divided by R2 plus. And the third combination. What is third combination here? Minus and plus is there. So minus Q1 into plus Q3 divided by the distance is that R3. So now afterwards we can simplify that, like minus Q1 Q2 by R1 plus Q2 Q3 by R2 minus Q1 Q3 by R3. So while finding the potential energy for the system of charges, it may be 3 charges or it may be n charges, n system of charges, we should write the combination of the charges and we should apply the sign convention. Original sign we have to apply in that formula, then we can calculate potential energy. Okay, so the potential energy of system of 3 charges. And next one is that potential energy of system of charges but in the presence of external electric field. So what we have discussed here, in the absence of external electric field. And next topic is that in the presence of external electric field, what will be the potential energy in the presence of external electric field? That we will see in next class.